We've talked quite a bit about how difficult it is to predict earthquakes and how we prepare for them. So today, let's take a tour of earthquake science. First up, we would, of course, love to have more warning when an earthquake is about to strike. But their origins are so deep within the Earth that there's not much up here on the surface for us to detect. Let's go over what few leads we do have.
On April 6, 2009, an earthquake struck near the Italian city of L'Aquila, killing nearly 300 people. It was a terrible disaster, and you've probably heard of it because 6 Italian scientists and 1 government employee were later tried and convicted on criminal manslaughter charges for providing inaccurate, incomplete, and contradicting information about the earthquake danger. They were sentenced to 6 years in jail, basically for failing to predict an earthquake. This has riled up a lot of folks in the science world, and with good reason, because while we know a lot more than ever about earthquakes, there is still no reliable way to predict them. Now, can we forecast where earthquakes are likely to occur over a long period of time? Yes. Of course we can. For example, scientists know that there have been 20 major earthquakes of magnitude 9 or higher in the Cascadia region between Vancouver and Central California over the past 10,000 years. The last one took place in 1700. There will be another in the future. Sometime. But can seismologists predict the time, epicenter, location, and magnitude of the next Cascadia earthquake? They cannot. There are lots of reasons for this, but it's mainly because it's so hard to study tectonic plates, the giant slabs of the Earth's crust that are always moving around, since they're usually at least 100 kilometers thick. So while scientists believe that quakes start when 2 or more plates meet, the process that occurs before they start is subtle and almost impossible to observe. That doesn't mean that there aren't potential indicators that can be studied or loads of intriguing anecdotal evidence that some people believe can help predict some earthquakes. For instance, many scientists think that rising levels of radon are a good indicator of an impending earthquake. A radioactive gas produced by the natural decay of uranium, radon builds up in cavities beneath the surface of the Earth and may be released by shifts in the ground preceding a quake. But while radon leaks have preceded some quakes in the past, in many instances they haven't. Others believe that changes in electromagnetic fields near fault lines indicate an impending quake. A Silicon Valley company called QuakeFinder has installed 200 sensors to measure changes in magnetic fields below the ground and to detect charged particles in the air. But the U.S. Geological Survey doesn't support the project, calling it a scientific dead end. Finally, almost everybody has heard of examples of animals predicting earthquakes. Examples go as far back as 373 BC. Back then, as the story goes, pretty much every critter hightailed it out of the Greek city of Helike, just 5 days before it was destroyed by a massive quake. And just 74 kilometers from L'Aquila, biologists studying toads reported that 96% of the amphibians abandoned their breeding site again 5 days before the 2009 disaster. Alas, as intriguing as they are, you never hear any of these stories before an earthquake strikes. While there might be something to this, strange animal behavior, like other precursors to earthquakes, is generally only observed in hindsight. Plus, it's worth pointing out that other studies have found that animals do not respond to the threat of earthquakes at all. A group of biologists was studying ant colony behavior in the Mojave Desert in 1992 when a 7.4 magnitude earthquake struck the region. The scientists reported that contrary to anecdotal reports of earthquake effects on ant behavior, the quake had no effect on the insects. So in order to predict an earthquake and in turn send out warnings of imminent danger to the public, you need reliable and repeatable indicators, and those just don't exist, yet at least. Until they do, we should probably stop throwing scientists in jail for failing to do something that's impossible.
In that video, we mentioned the widespread reports of animals predicting earthquakes, and that leads to even more questions. So then we did a whole other video about that. See, we're not sure how animals do it, or even if they really can. But a lot of people want to find out. Here's more on how they might be doing it.
In 2011, around 3 weeks before a magnitude 7 earthquake hit Peru, mammals and birds reportedly started clearing out of a national park in the Andes. You've probably heard stories like this before, about animals that seem to somehow sense an earthquake coming. Unfortunately, a 2018 review of more than 700 of these reports found that most of them were just anecdotes or single observations. They couldn't really be backed up scientifically. So, recently, different groups of researchers have been trying to get to the bottom of this claim for real. They've been trying to figure out if there really are changes in animal behavior before an earthquake and what could possibly explain them. Now, you might think, given the hundreds of times people have reported that animals were behaving oddly before an earthquake, that there must be something to it. But the problem is, humans are pattern-finding machines, and we're also prone to a psychological phenomenon known as hindsight bias, where we think things that happened make sense after they happen, but not beforehand. We kind of can't trust our memories. So instead of looking back after an earthquake happens and trying to remember what animals were doing, it's better to track animal behavior over a long period of time. That way, when an earthquake happens, we can use data to compare animal behavior before and after. And in a few cases, scientists have actually been able to do that. For example, in 2014, researchers at a farm in Japan tracked the amount of milk a few dozen cows were making each day, which might sound like a weird metric, but since most farm animals get milked at least once a day, it was an easy way to monitor their behavior. And the study found that on average, cows produced less milk in the 3 weeks before an earthquake. Authors could not explain why that was happening, but it wasn't the only study that measured a change in the behavior of farm animals before a quake. A couple years later in Italy, researchers in a separate study mounted accelerometers on a farm's cows, sheep, and dogs to track their movements over a few months between 2016 and 2017. They basically put Fitbits on them. And the data showed that about 5 hours before a quake hit, the animals' activity patterns did change significantly. Not only that, but the closer they were to the earthquake, the earlier their behavior changed, possibly because whatever signals they were detecting were stronger. The results were interesting for two reasons. First, they suggested that it might be possible to set up some kind of early warning system for earthquakes using, of all things, farm animals in different locations. But second, they showed that it wasn't enough just to track a single species. A good prediction required data from multiple animals that captured how they interacted with each other. And soon, we are actually going to have a lot more data like that. At the beginning of 2020, scientists from Germany and Russia launched a project called Icarus that tracks the movement of thousands of birds, mammals, and insects across the globe. Rather than just looking at what one animal or a small group of animals is doing, the idea behind Icarus is to use computer algorithms to analyze big patterns of movement. To do this, researchers plan to tag thousands of animals with small transmitters that regularly send information on their location, activity, and local weather conditions to an antenna mounted on the International Space Station. It is an enormous project. And right now, it's still in its test phase, but the goal is that by the end of 2020, researchers will be able to start gathering data and seeing how well it can be used to predict earthquakes and other natural events like volcanic eruptions. All of these findings are pretty exciting, and recent advances in things like artificial intelligence and satellite technology have made these sorts of studies easier. But despite all of the evidence that at least some animals may be able to sense earthquakes well before they happen, we still don't know how they're doing it. Some scientists hypothesize that animals might be sensing vibrations in the earth from movements in the crust right before a quake, but there's no strong evidence for that. However, it's also possible that animals are picking up on other environmental events that are triggered by that movement in the crust. For example, the air can become electrically charged as the squeezing and shifting of the earth break chemical bonds in minerals, releasing charged atoms into the air. Some animals may be able to pick up on that change in the air itself. Those charged atoms can also dissolve into water, turning the water acidic. And we know that, for instance, amphibians are super sensitive to changes in water chemistry because their skin is permeable, which could explain why a whole bunch of toads fled their regular breeding pond 5 days before the 2009 earthquake in LAquila, Italy. Scientists who observed this behavior didn't measure the water acidity, so we don't know for sure, but at least it's plausible. And as we learn more about how animals behave around earthquakes and how they might detect the early signals of them, we may be able to better protect ourselves from the disasters they cause. Whether it's by setting up a network of farm animals or building sensors that mimic certain animals' abilities, perhaps we can learn from them how to predict earthquakes on our own.
So, there's still a lot to learn, but we might be able to rely on something a little more solid and less flighty than the neighborhood pigeons. Math. Glorious math. Because there's a well-known mathematical function that seems to mimic the unpredictable and erratic nature of earthquakes. Let Hank give you the details.
Science isn't just about explaining the natural world, it's also about taking those explanations and using them to make predictions. Predictions can save lives, but there are some natural events that, so far, we just cannot forecast. For example, devastating earthquakes happen every year, and even though scientists broadly understand why, they've never successfully predicted one. But as erratic as earthquakes seem, they do appear to follow one odd mathematical pattern known as the Devil's Staircase. Which is a thing that is about as bizarre as it sounds, and yet this strange combination of geology and abstract math could point the way to better earthquake predictions. Powerful earthquakes are relatively rare. On average, there are about 16 each year. And traditionally, we've understood that they happen as tension builds up along a fault in the Earth's crust and then gives way. However, we never know when that will happen. Today, scientists are able to predict the average number of events that will happen during a given period, but not when or where they will happen, which might help governments budget for disaster relief, but does not help governments issue like evacuation warnings. Earthquakes might not be as random as they seem, though. In a 2020 study, a team of researchers noticed that these events loosely follow a well-known pattern called the Devil's Staircase. It's more properly called the Cantor function, after the German mathematician Georg Cantor, who discovered it in 1883. At almost any point you pick, the Cantor function is flat, but there are also spots where it rises in a bunch of steps that are all really close together. And it works sort of like a fractal. If you zoom in on any given part, the Cantor function looks basically the same, with long periods of inactivity interrupted by short bursts of activity. Like a really terrible staircase. But it actually turns out to be pretty useful for representing some things in nature, especially the behavior of certain highly connected systems, like brain cells. For instance, scientists have used this function to explore why certain brain activity might trigger a seizure. It's useful because small changes to these systems happen all the time and mostly have very little effect. That's the flat part of the function. But when something big does happen, it can often trigger more big events that happen one after the other, like a series of quick steps. The researchers observed patterns of earthquakes in several regions around the world and found that a number of them seemed to follow the Devil's Staircase, including in the western US, Australia, and off the coast of Algeria. Basically, within certain regions, tectonic activity in one part of the crust can trigger new activity nearby. Their analysis suggests that in these areas, short bursts of strong quake activity happen more often than you'd expect from traditional modeling. That's likely because traditional models focus on the tension at a single fault, but in these areas, the time between bursts seems related to the amount of strain on broader regions of the Earth's crust. So a model that treats each fault individually seems to be missing the bigger picture. Unfortunately, all that interconnectedness leads to cycles that are less predictable than we'd hoped, so it's not a huge step forward in predicting future events, but recognizing that powerful earthquakes happen in bursts could help us understand what actually happens at a fault. And that could pay off big in the future. After all, it doesn't seem likely that earthquakes are truly random events. They're just processes that are so complicated that we haven't figured out what factors really matter. In the case of earthquakes, the devil really is in the details.
So the world's worst staircase can help us understand when nature is about to shake all the water out of the swimming pool? Neat. But it would be nice if we could protect our swimming pools from earthquake damage, not to mention all the other important structures that people rely on. Luckily, engineers are a lot better at protecting structures than we are at predicting earthquakes in the first place. In this next video, Olivia explains how engineers are working to earthquake-proof buildings.
Nature has an entire suite of disasters at its disposal, and some are more difficult to predict than others, like earthquakes. Earthquakes are basically impossible to predict with any real certainty. So populations living on or near fault lines are constantly on the lookout for the next big one. Still, it's not like we're just sitting around twiddling our thumbs waiting for it to strike. Engineers have already developed some pretty amazing inventions that help protect buildings during quakes. And they're working on more. Here's what they have in their arsenal now, along with a sneak peek of what's on the horizon. Today, there are a few main ways we try and protect buildings from earthquakes. One is to keep buildings from shaking side to side as much as possible. And that can be done in several ways. Many huge skyscrapers utilize massive swinging balls, aka tuned mass dampers. They're large pendulums placed high inside buildings, and they sway in response to any movement the building makes. That counteracts whatever is happening outside. The most famous building with one of these is probably Taipei 101 in Taiwan. For shorter buildings, engineers often choose a different route. They isolate the base of the building from the ground using a system of rubber and lead that serves as a shock absorber. A major airport in Turkey uses this method, and it's one of the largest seismically isolated buildings in the world. It uses 300 separate isolators that can reduce the side-to-side oomph the earthquake puts on it by 80%, which is impressive. Still, while tuned mass dampers and shock absorbers are great, they're not perfect. So engineers are also exploring new options to really step up their game. Some of this research builds off of existing ideas. For example, in 2015, one group proposed a new system called vibrating barrier, which is like a super strong version of a regular shock absorber. You start with a weight held in place by springs. Then you stick it all in a box and bury that box under the building's foundation. When an earthquake comes along, the weight gets jostled around and in doing so absorbs the vibrational energy that would otherwise hit the building. This kind of tech would be perfect for buildings you can't modify, like historical landmarks. But it isn't ready to go prime time yet. You still have to calibrate the system to absorb a certain frequency, which is specific to each building. That's because depending on the building's mass and what it's made of, there are going to be some frequencies that make it vibrate more than others. So you'd need to use springs of a specific stiffness. More massive buildings would need more massive dampers. Still, models suggest this could do a lot of good. Some experiments report that this system could reduce the amount of acceleration a building is subjected to almost 90%. Also, they could protect multiple buildings at once, so they're totally worth researching further. Of course, there are 1,000 ways to solve a problem, so other teams have approached this earthquake challenge a little differently. For example, one major field of research involves investigating how to strengthen the buildings themselves. Some of that involves using fancy new construction ingredients like carbon nanotubes. But there's another way to go about it too. Like in 2018, a team at Purdue announced that they had been 3D printing cement paste into specific shapes and patterns to improve the concrete's response to earthquakes. They're calling these patterns architectures, and they're capable of carefully directing pressure that could induce cracks. So even though damage does happen to the structure, the overall damage is minimized. What's really cool, though, is that these architectures are inspired by nature, specifically by the shells of arthropods. For example, the mantis shrimp has a giant claw to smash its prey at blinding speed. To avoid having this claw develop one huge crack, it's structured in such a way that micro cracks form in a specific helical pattern that distributes the pressure over a larger area. That makes the claw less brittle overall, and now those helical patterns are being used in construction. Admittedly, this research is pretty new, so it's going to take some time to figure out exactly if and or how it will be incorporated into future buildings. But it's pretty awesome that our solution to a natural disaster could come from nature itself. Now, vibrating barriers and nature-inspired materials are cool, but they might seem pretty standard in the world of engineering. So if you've been holding out for a really weird, wonderful example, we have one of those for you too. I'm talking earthquake invisibility cloaks. Here you have a series of concentric plastic rings built into the foundation of your building of choice. Each ring has its own specific stiffness and elasticity to absorb a certain frequency of wave. When an earthquake hits, the rings deform and deflect some of the quake's energy along themselves, moving that energy around the building so that the people inside never even feel a thing. Basically, the building becomes invisible to earthquakes. I mean, this isn't great news for the next building over if it doesn't have its own protection, but I guess this technology lives in a world where it does. The more rings you have, the more frequencies you can cover, and you don't necessarily need 100 of them either. You just need enough to take care of the most abundant frequencies, and the ones the building is most sensitive to. Also, as a huge bonus, these rings don't have to be massive. For a 10-meter wide building, each ring would only have to be about 10 centimeters thick. This technology started getting attention around 2009, though, so there are obviously a few things to work out before it starts popping up in the real world. But like the other developments we've talked about, it is really promising. At the end of the day, the Earth isn't going to stop throwing earthquakes at us. But these kind of innovations mean that maybe one day we won't have to worry too much about the next big one.
But what if the next big one is real big? Because I don't want to scare you, but geologists think there might be a megaquake brewing in the Pacific Northwest. Don't freak out though, because there's a surprising amount we can do to prepare.
If you live in the US, you may have heard that the Pacific Northwest is supposedly overdue for an earthquake of colossal, devastating proportions. It is true that a so-called megaquake is building beneath the region, and it's something we'll someday have to deal with. And while we're not exactly overdue for a disaster, the better we understand the threat, the better we can prepare for the day it comes. Earthquakes are caused by the movement of the Earth's tectonic plates, rigid slabs of slowly moving crust beneath the surface that fit together like puzzle pieces. As the plates shift, they push and grind against one another, creating rifts and mountains and putting a lot of stress on the rock beneath our feet. This mounting pressure eventually gives way, and the rock slips along fractures called faults. All at once, the stress is relieved, and the energy gets released in waves that ripple outward in all directions. That's an earthquake. Small earthquakes happen literally every day, but they don't make the news because we don't actually feel most of them. The size of an earthquake is expressed using a relative scale called magnitude, and people generally can't feel earthquakes below a magnitude of 2 or 3. These everyday quakes tend to originate on fault lines less than 70 kilometers underground, so they're called shallow earthquakes, and usually they're pretty harmless. Some shallow earthquakes can be pretty severe though, like the magnitude 6.4 quake that hit Coalinga, California in 1983. The vibrations caused damage to hundreds of buildings and set off fires that added to the destruction. In all, it caused about $50 million worth of damage. In general, the magnitude of an earthquake depends on the size of the fault and the amount of movement in the crust. The bigger the fault area, the bigger the earthquakes it can produce. The famous San Andreas Fault in California is particularly impressive. It's more than 1,200 kilometers long and about 16 kilometers deep. It's capable of producing extremely powerful events like the catastrophic San Francisco earthquake in 1906, a magnitude 7.9 quake that shook all of California. But there's a limit. It's extremely unlikely that this fault would ever cause an earthquake stronger than a magnitude 8.3 at worst. The very biggest earthquakes happen at the most dramatic faults. These exist at places called subduction zones, where instead of two plates sliding horizontally past each other, an oceanic plate runs into a continental plate and slides down underneath it. This motion causes a lot of stress on rocks, and these are the only places where you can get what are called mega thrust earthquakes. These are massive earthquakes that release truly ridiculous amounts of energy. These earthquakes are rare, but they include the most powerful earthquakes in history, such as the 2011 Tohoku earthquake in Japan and the 1960 Valdivia earthquake in Chile, both of which caused catastrophic damage. The Tohoku earthquake reached a magnitude of 9.1, and the Valdivia quake was the biggest in recorded history at magnitude 9.5. A magnitude 9.5 might not sound like a huge jump from, say, Coalinga's 6.4 magnitude quake, but earthquakes aren't measured on a linear scale. They're measured on a logarithmic scale. That means that every time the magnitude increases by 1, the amplitude of the waves increases tenfold, and the earthquake releases 32 times more energy. That makes the Chile megathrust earthquake more than 44,000 times stronger than the quake in Coalinga. And right now, an earthquake of this size is brewing beneath the United States. The Pacific Northwest sits right on top of the Cascadia subduction zone, where the Juan de Fuca plate is sitting beneath the North American plate. Tectonic movement in this area has created a lot of faults and caused many earthquakes and tsunamis. It's also created the volcanoes in the Cascades. But the biggest fault in any subduction zone is the boundary between the tectonic plates themselves. The Cascadia subduction fault is 1,000 kilometers long, running from under southern British Columbia down to northern California, and dipping hundreds of kilometers down below the surface. It's a megathrust fault. In the deepest parts of the fault, the plates move slowly and steadily as warmer temperatures make the rock more flexible. But in the upper 30 kilometers of the fault, friction causes the rock to get stuck. The plates lock, and stress builds and builds until it finally slips, releasing a huge megathrust earthquake. Something like this is building in Cascadia, and we know because it's happened before. The last Cascadian megaquake happened in the year 1700. No one recorded that earthquake on any sort of scientific equipment, but it left behind enough evidence on both sides of the Pacific Ocean that geologists have been able to learn a lot about it, including the date and time that it happened. In North America, geologic evidence along the coasts of Oregon and Washington points to a dramatic event just over 300 years ago. At that time, the stacked layers of peat left behind in coastal forests are interrupted by a layer of ocean sediment that washed ashore with one or more large tsunamis. And on the sea floor, geologists find layers called turbidites, massive piles of sediment and debris left behind by underwater landslides. These simultaneous tsunamis and landslides point to a massive earthquake that shook up the entire coastline. Scientists have even found the remains of trees that died in that event, and they've used tree ring dating to narrow down the timing to late 1699 or early 1700. This lines up with stories from native people about shaking and flooding in the area. And across the ocean, that time frame also lines up with Japanese legends of an orphan tsunami. In Japan, tsunamis generally come after people feel the earth shake, but one day, a tsunami struck with no warning. That happened right around midnight on January 28, 1700. Knowing that it takes about 10 hours for a tsunami to travel from the Cascades to Japan, geologists estimate that the earthquake hit around 9 p.m. local time on January 26, 1700. There are records of the damage that tsunami caused in Japan, and they tell us the earthquake was a big one, most likely a magnitude 8 or 9. A megaquake. And it's not the only one. Similar geological evidence in the Pacific Northwest shows that several huge earthquakes have struck the region over the last several thousand years. For millennia, the Cascadia subduction zone has been going through cycles of slowly building up stress, then cracking and releasing enormous earthquakes. For more than 300 years, that energy has been building, and someday, it'll give again. But earthquakes don't exactly happen like clockwork. On average, these quakes have struck every 500 years or so, but the intervals vary from 200 to 1,000 years. That makes it very difficult to predict when the next huge quake will be, and we can't exactly say that we're overdue for the next one. But those who think we have some predictive power give it a roughly 10% chance of happening within the next 50 years. Whenever it happens, it won't be pretty. A magnitude 9 earthquake would cause several minutes of intense vibrations throughout the Pacific Northwest, taking down buildings and causing as much as several $1 billion of damage. Then after the main earthquake, large aftershocks would rattle the coast again, possibly knocking down weakened structures that survived the first round. Within 30 minutes, tsunamis up to several meters high would wash ashore, threatening over 71,000 people currently living in the inundation zone. And over the following hours, the waves could reach Alaska, Hawaii, and even Japan. The megaquake would damage roads and airports, making it difficult to evacuate people or get emergency assistance where it's needed. And the Pacific Northwest isn't nearly as prepared as we'd hoped. Since the history of these huge Cascadian earthquakes was only uncovered in the past few decades, the cities in the region weren't built to handle such an event. Many of their buildings, for example, are built of heavy brick and concrete without steel beams for reinforcement, which makes them likely to collapse during strong vibrations. And historically, these communities haven't set up standard earthquake evacuation procedures. So that's slightly terrifying, but I have good and bad news. The inevitable catastrophe isn't actually the biggest earthquake threat to the Pacific Northwest. A megaquake will certainly be a disaster when it happens, but in the meantime, shallow earthquakes, like the ones that happen along the San Andreas Fault, pose a more immediate threat. These earthquakes happen more frequently, and while the Cascadian megaquake would most likely happen offshore, smaller earthquakes often strike further inland, which makes them a serious danger for big cities like Seattle. Now, don't go thinking that the Pacific Northwest is just doomed. Even though we can't predict with precision when earthquakes will hit, there's actually a lot we can do to prepare for quakes, mega and otherwise. For one thing, scientists are working hard to understand hazard areas. That includes scoping out flood zones that might be most vulnerable in a tsunami, roads that might be in paths of landslides, and unstable soils that could weaken during an earthquake. This knowledge helps emergency management groups prepare for the impacts of an earthquake. Already, building codes in the Pacific Northwest have been adjusted to account for the threat of earthquakes. Older buildings are being reinforced with steel bracing to prevent structural collapse, and newer buildings are often built on flexible bearings called base isolators, which can absorb a lot of the energy from a quake. At the same time, evacuation routes are being mapped out to allow citizens to get to safety in case of disaster. Scientists are also working on early warning systems. A study published in 2019, for example, found that it might be possible to predict the magnitude of an earthquake from its very first minor waves. We're only talking a few seconds warning, but even so, this early detection could make it possible to get information out to the public. Other groups are working on ways to fast-track these warnings to the people who need to hear them. For instance, an early warning system called Shake Alert is working on detecting earthquakes and alerting people seconds before the shaking even reaches them. The system is currently being tested in places like hospitals and transportation facilities along the west coast of the United States. A few seconds might not sound like much, but it's enough time for people to take cover, move away from dangerous objects like glass or chemicals, and to slow down cars, trains, and taxiing planes. Even with all this technology, the most important safety measure is still public education. Communities that understand the risks can do much more to keep themselves safe. For instance, in 2010, a magnitude 8.8 earthquake struck Chile, and by the time the tsunami reached the coast, most residents were already heading for higher ground, saving their own lives. Now, in the Cascadian region, people are practicing safety measures like evacuation drills and tsunami siren tests. There's also plenty of information on what you can do to prepare yourself. So if you live in the Pacific Northwest, or anywhere with a significant earthquake risk, find out what you can do. Check out your local geological agency resources and look at the links in the description of this video. The next Cascadian megaquake is brewing beneath the surface right now, and so are similar earthquakes all around the world. But we know more about earthquakes now than we ever have. And as we keep learning, we'll be better prepared to protect ourselves from the next one.
So maybe we can't predict this big one far in advance, but we can still be prepared. And the more we learn about how to predict other earthquakes, the more prepared we can be in the future. Thanks for joining me today on SciShow. If you'd like to keep watching, you might also like our episode on mega tsunamis.